is based on the topic of ITER, and that's exactly where the name of our video originates from, because the meaning of the word ITER means the way in Latin.
And finally, about our project, we want to add that we were helped by classmates, and this is the reason that even though it might seem professional, I guess, the project is created by students only. And yeah, another fun thing is that the younger version of me in the film is my actual brother. And that concludes it from us.
Thank you for your interesting presentation. And now we can go on watching your video. When Emilia, you're ready, you can share it.
Нека ти покажа колко възможности ти предоставя нашето училище. Това е кабинета по литература. Ако искаш да ставаш журналист или писател като мен, това е място за теб.
Не мисля. Каква е тази стая?
Това не ти трябва. Кабинетът е визитно. Не е място за деца като теб. Ядни глупости, атоми, планети, вълни. По-добре нещо по-практично. Може би стаята полети. Искаш ли да покажа моята глупостта? Не щом да изглежда специалист. Ще съм горда да познавам.
Или пък иди.
Здравейте! Търся Георги Игнатов, ръководител на първи отдел. Аз съм Симона Вутова от телевизия Гама.
Да, аз съм Георги. С какво мога да ви помогна?
Имам няколко въпроса за вас. Трябват ни само 5-10 минути. Така, годината е 2035 и мечтата за ефтината и чиста енергия, от която планетата ни така отчаяно се нуждае, вече се превърна в реалност. И вие сте част от този амбициозен проект. Какво представлява ИТЕР?
Слънцето е един неизчерпаем източник на енергия, нали? Ние направихме свое собствено второ слънце. Това е ИТЕР. Реактор, който пресъздава сливането на водородни атоми в ядрото на Слънцето и останалите звезди, или така наречения термоядрен синтез.
И с какво той е по-различен от останалите?
Безвреден е. Суровините, необходими за добиване на енергия, са само двата изотопа на водорода. Deutерий, който се среща в морската вода, и тритий, който добиваме от силиция. Сместа от двата се грява до 150 милиона градуса, състояние на плазма, която се контролира от свръхмощно магнитно поле. Освен това не се отделя никакъв въглероден диоксид при процеса, което не замърсява околната среда.
Кое беше най-голямото препятствие по пътя към реализирането на този проект?
Целта беше да получим повече енергия от тази, която сме потребили за загряването на водорода. И успяхме след години опити.
А как се зароди идеята? Как започна всичко?
Аз съм сред новите попълнения на екипа. Историята на ИТЕР започва още през 50-те години на миналия век. При мен обаче започна доста странно.
Разкажете ни.
Едно момиче в училище ми каза, че физиката е прекалено сложна и не си струва. Особено ядрената. И това също ме мотивира да стана физик. Защото само така ще помогна в изграждането на по-добра бъдеще за планетата ни. А и толкова различни държави обедниха усилията си и вложиха средства в ИТЕР. Света се събра в името на обща кауза. Има ли нещо по-хубаво от това?
So thank you, Confusion, Team Confusion for your video too. Very nice video. I remind you all participants that sometimes if the video quality is not the best, unfortunately it doesn't depend on us. It depends on connection, server, and so on. So you can find it and watch it with no rush in the In an Association YouTube account. You can find all the fantastic videos the students prepared for the nuclear competition. So now, if there are any questions from the jury member, yes, Lizanne, please.
Hi, congratulations with your video.
Thank you.
I'm really impressed about the movie, and I think it's very nice that you even include your younger brother to be involved in this movie. So my question for this is, do you think it's possible to reach out to the younger generation, the younger generation, so the kids 10 to 12 years, and how would you do that?
Well, of course, we can reach to the younger generations, mainly with videos like this one, or even I will dare to say the team from Nuclear, the other team from Bratzo, which made a really fun video, but especially for the younger generations, such fun way of displaying things, they get it much more easier this way. And if you can get their attention, they will start to invest in this sphere themselves too. So the most important is to catch your attention, give them the basic facts, and they will do the rest.
What was the impression of your brother? Did he like it?
Well, yes, me and my brother are actually very close. And so there was this one time where I even tried to explain him why would the balloon would blow up if you heat it enough. So yes.
Okay, that's nice. That's real. Thank you. Well done. Thank you.
And so there are any other questions? Leon, I don't know if your hand is raised up since before. Yeah, okay, no.
Any other questions?
Any other questions for the Confusion team? If not, we can move on. But before, we have to send a great applause to the Confusion team as well. So congratulations again, guys, for your work and your project.
Thank you very much.
Then we have to go on with the Anfre team from Spain. I saw you before. Yes.
Hello.
Hello. When you're ready, you can start sharing your screen in your presentation.
Okay. Oh, wait. Okay, can you see it now?
Yes, it's okay. You can go. You can start.
Okay. So we are the Ampre team. Our names are Alfredo Gonzalez
and Andrea Ciudad,
and we're students of the Scientific Baccalaureate at Colegio San Jose from Ciudad Real in Spain. First of all, thank you so much for organizing this course and giving us the opportunity of being on it. And now we're going to start a presentation with our country.
Spain belongs to the western part of Europe, and it is also part of the European Union. It occupies most of the Iberian Peninsula, the Canary Islands, the Balearic Islands, and two autonomous cities, Ceuta and Melilla, which are located in the north of Morocco. The capital of our country is Madrid, which is located in the center of Spain. Our autonomous community, Castilla-La Mancha, is located just below said community. One of the most important characteristics of our country will be the variety of culture and the different co-official languages, since we have three in addition to Spanish. The typical gastronomy of each community, there are 17, the music and dances of each region. The development of nuclear energy in Spain began in the 1960s with the construction of the first nuclear power plant. Spain currently has several facilities to cover the complete cycle. 7 operating nuclear reactors, a nuclear fuel factory, and a very low and medium activity radioactive waste storage center. However, there are only 2 universities to study nuclear engineering, the Autonomous University of Madrid and the National University of Distance Education of Industrial Engineers. Our city is called Ciudad Real. It is a small town with 80,000 inhabitants. Spanish is spoken from all the official languages. It is a volcanic area called Calatrava. Among the culture that characterizes us, we have the seguidillas, which is a traditional dance, and the migas as the main dish that is based on bread accompanied by pepper and meat. The history of our city is quite surprising, since all the three monotheist religions, Judaism, Christianity, and Islam, lived together during the Middle Age.
Now with our school, it was founded in 1889 and it was directed by the new institution of the Daughters of Charity of San Vicente de Paul. The school turned into a center for girls of all social classes and of a superior culture. During the years of the Civil War, the school was transformed into a blood hospital. The sisters, welcomed by families from Ciudad Real, rendered service caring for the sick. Nowadays, it's a Byzantine center with the education mission of integrating the person into society. And what we have learned about nuclear sciences in school, the topic of nuclear energy was very brief and focused mainly on the basis of this energy and the formula to calculate the heat energy obtained by fission. Because of this, most of the information that we have used during this project was obtained from the internet by doing our own research.
Our decision to participate in the project begins with the presentation of the context on the potential and the aspect of nuclear energy by our English teacher. Since we still do not have anything clear about what we want to study except engineering, we decided to base our work on how we would like to have described nuclear energy to choose this type of training. Moreover, we were encouraged to continue with this work by our concern to learn, since our notion about nuclear energy's development, use, etc. was very basic, and this increased our curiosity, wanting to learn from what nuclear energy is in itself to the job developments or the security of it. After having completed the project, we can say that we are very happy to have participated, since it has opened up a completely unknown job option for both of us, and from which we are qualified because it is necessary to work under planning with a team and having a schedule.
Before we move on into the video, I would like to explain how it's done. First, our work is focused on defining what nuclear energy is and to show that the myths that exist about the pollution are not real. The development of the work of the nuclear power plant, the different steps into which the work is divided to produce this type of energy, and the elements that intervene in each of the steps so that a person can consider whether they have the skills required for this type of job. Next, it's uses, the other branches of science of the human field where nuclear energy is used to raise awareness that this type of energy is very necessary for our daily lives, much more than it seems. Next, security, the protections available to the worker and the nuclear plant to avoid risk, although there is a very low incidence of cases. And finally, the recycling of the energy, denying all the beliefs about its contamination. Thank you very much for your time.
Thank you for your presentation. And then Emilia, we can go on with the video once you are ready, please.
If someone asked you about nuclear energy in the future, you would think about something like this, right? What if I told you that nuclear energy is one of the cleanest energies for the environment? You wouldn't believe me, would you? Despite the controversy, nuclear energy is the only source capable of supplying large amounts of electricity without emitting greenhouse gases. The image of its towers cooling by emitting what looks like smoke, although it's nothing more than water steam. But what is nuclear energy? It's the energy released as a result of the reactions produced in the nucleus of an atom, formed by neutrons and protons. These reactions can be either nuclear fission and nuclear fusion. In nuclear fusion, the energy is released when the nucleus of the atom combines. In nuclear fission, the nucleus separates and thus releasing energy. They produce a large amount of heat energy and radiation, which is then used to produce steam electricity, among other things. Nuclear technological advances can be applied in many sectors. In medicine, it's used to detect and destroy tumors, as well as to treat cancer. According to a 2013 NASA study, nuclear energy has prevented around 1.8 million deaths. In art and archaeology, it's used both for dating and to eliminate insects or fungi. In mining, it's used to determine the presence of oil or minerals. In agriculture, it's used to create mutations in plants and increase food preservation. And in space and cosmology, to determine the age of the universe, and also as a rocket propellant. A nuclear power plant is a facility in which electricity is generated from heat energy produced by fission reactions in a nuclear reactor and where the nuclear fuel is housed. The process can be simplified into 5 phases. The fission of uranium takes place in a nuclear reactor, releasing a large amount of energy that heats the water until it evaporates. This steam is transported to the turbine generator unit. Once there, the turbine blades rotate by the action of the steam and move the generator, which transforms the mechanical energy of the turbine's rotation into electricity, ready for industrial use. When the steam has passed through the turbine, it is sent to a condenser where it cools and becomes liquid. Afterwards, the liquid is transported to get steam again, thus closing the water circuit. Recycling the management of nuclear waste is one of the hardest parts of using nuclear energy, since it's dangerous and difficult to dispose of. However, with the development of the first nuclear plants, solutions for toxic materials had already been implemented for waste treatment. Radioactive waste is the residues that are contaminated by radioisotopes, and there are 2 types. Low and medium waste activity, which is mixed with concrete and placed in drums that are stored at the nuclear plant itself, and high-level waste, that is stored temporarily in the central in concrete pools with water. Later, it will be reprocessed to use it as fuel, nuclear weapons, and to be encapsulated. Nuclear safety is used to minimize the radiological risk of the facilities to achieve adequate protections for workers, the public, and the environment. Some security measures carried out are the analysis to find an ideal location, considering the characteristics of the area and possible adverse effects, in a final study in which it's detailed that the radioactive products generated are protected by 4 consecutive barriers. The building systems components related to the reactor and radioactivity containment are resistant to the maximum natural events that can occur. There are safety systems like duplicated and independent components for safety-critical systems, electricity and water supply lines to prevent accidents or failures. The control panel is protected against possible sabotage and has fire protection systems. The manufacture, installation and assembly of components are carried out according to a very strict quality program. The chances of an accident occurring are really low, since the mass that is used is very small. Finally, the radioactive emissions produced in a nuclear power plant do not exceed those produced naturally. For this and all that it has to offer to us, trust nuclear energy.
Thank you, Tim Humphrey, for your video. Very nice cartoon movie explaining the importance of the nuclear energy. And now the floor is to the jury. So if there are any questions from the jury, please, it's your turn. Let me see if there are some hands raised up.
Hi, Mattia, I'm raising it up physically.
Okay, I see you, Paco. Please go on.
Hi, thanks, Mattia. Well, congratulations to the team. I'd like to make two points. The first one is about the possibilities in Spain to study nuclear, and it's very interesting that you brought this topic up, because we think we need to take a note of this. You mentioned, if I'm not mistaken, Autónoma de Madrid and UNED, yeah? So in my personal experience, I'm also from Spain, and I studied nuclear engineering later on outside Spain. And when I did that, I thought that it was only possible in Politécnica de Catalunya, okay? So I also experienced like some kind of, I'm not really sure what programs are in Spain. And it turns out that apart from Autónoma and UNED, Politécnica de Madrid also has nuclear program, Politécnica de Catalunya has Valencia and Sevilla. But I discovered this really late, to be honest. And I think it's good that you brought it up, because I think we need to make a point or how to address the possibilities that we have in Spain so that they reach the schools also, because this thing exactly happened to me as well. So it was nice that you addressed that point, but be informed that we actually have a few other programs. And regarding now your work, I think it was fabulous that you mentioned the need to clarify the myths and the controversy. That's much appreciated. So you can kind of feel proud to have done a contribution in that. And I think that you went for a very big scope of things. So I guess that you've seen how many different fields are actually playing in a power plant, and you've addressed safety systems, a lot of things. So with that, it's a clear effort that you went to a big scope, and congratulations on that. Now, obviously, because I have to ask a question, what part of all of these topics that you spoke of was the one that you found most interesting?
Well, we didn't thought that nuclear energy had so many steps in the security process, but obviously after all the incidents, we found out about all the process, and it was really surprising to us that after uh, these incidents, they have taken this effort to try to make nuclear again a trustable energy.
Thank you. Interesting.
Any other question from the jury? For the team Ampre? Yes, Walter, please. Oh no, sorry, you are uploading.
No, okay, but anyway, I wanted just to pay compliments for the very nice presentation and also the very nice movie that you have set up. Just a question could be, let's say, what share of your own work is there? Let me say, and how much you relied on your teachers, for instance, for setting up this, because it was very nice. What about the cartoons, for instance? Did you make themselves, or let's say someone helped you?
An app for all the images, the cartoons, everything was made by an app. It's called Animaker. So we had to set everything up, but we didn't need help from our teachers. It was all made by us.
Okay, so best congratulations. It was really nice and very complete and extensive. So thank you very much. It was very, very nice.
Thank you also, Walter, for your question. Yes, we can gather also to your applause to make again a big congratulations to the team Ampre for their presentation, their work. And then we are moving to the last team.
Mattia, there's one hand from Leon. I saw it disappeared now. Okay.
Oh, sorry.
It's okay. Just continue. I'll have a comment at the end, not a question. Okay, if there will be time.
I'm sorry. I misunderstood with the previous hand that remained up. I'm sorry. So, but if you want to add some comments, Leon, please. We can.
I can do it at the end. So let's go with the.
Okay.
It's not a question to this team. So.
Okay. So now the last team, as I said, PhD from Croatia. I can see Katarina here. And if you're ready, you can start sharing your screen. Okay. And also Laura, I think from the same team. Yeah. Okay. Please, girl, the floor is yours.
Yeah, hi. So while Katarina puts up the presentation, I would just like to say that both of us are in self-isolation because the girl in our class has the virus. So I hope it won't be a problem, but if we have some technical difficulties, please bear with us. Okay, so the name of our team is PRHG. We weren't very creative. It's the name of our school, so we just named our team after that. So I am Katarina, this is my classmate Laura, and now we will tell you something about the process of making our video. Our mentor is our chemistry teacher, Professor Marina Lorbe-Božanić. So we come from Croatia. It's a country at the crossroad of Central and Southeast Europe on the Adriatic Sea. Since the Croats arrived here in 6th century and a lot of cultures had impact on them, today we have a very diverse culture. And on the other hand, in the science field, a lot of scientists who made great discoveries were born here, such as Nikola Tesla, Ruđer Bošković, Andrija Mohorovičić, Lavoslav Ružička, and many others. Besides the rich history and great inventors, one of Croatia's greatest wealth is nature. We have beautiful sea, lakes, rivers, caves, plains, mountains. So whatever your heart desires, you can find in Croatia. And if you haven't had a chance to visit already, we hope that you will one day because it pays off. The city where we come from is called Rijeka, which in English would be translated as river, because as you can see, it's a city that lays on small river Riječina, so that's why it's called Rijeka. It's third largest city in our country. It's located in Primorje-Gorski Kotar County on Kvarner Bay and inlet of the Adriatic Sea, and its principal seaport. This is also in Rijeka in the last few years, not very much, but in history it was, industry was very developed. And so this is a place where a great discovery was made. So this is the town where the first effective self-propelled naval torpedo was developed by Robert Whitehead and Giovanni Lupis. Today, it's a city of pretty sights and interesting people. And in 2016, Rijeka was selected as the European Capital of Culture for 2020. So last year, we had a lot of programs that were happening here, even though there was Corona. Here you can see our school that's called Prva Riječka Hrvatska Gimnazija, or short PRHG. And it was founded in 1627. Since then, the program changed a lot, but it's still one of the best, I dare to say, the best school in Rijeka. And today it offers 3 programs for its students: general, language, and sports one. Laura and I are in the general one, and we just finished 3rd grade there. Our students are included in many different projects, and they accomplish great achievements in many fields, but Laura will tell you more about that, so I'm giving the word to her.
Okay, so the students of our school have many opportunities thanks to the teachers who are willing to include us in our school community, but also the community of students from around the world. This year, it was a bit more difficult to do that. We still participated in Erasmus projects, debates, sustainability projects, and projects that help our community, all online, of course. But the 2 of us were the happiest when we did chemistry and biology projects, and also sometimes physics projects. When it comes to nuclear energy, we didn't do much just because that's something we learn in 4th grade of secondary school, and we just finished grade 3. Despite that, we did a few experiments to celebrate Mole Day in our school, and when pandemic wasn't a thing, we visited kindergartens where we demonstrated different chemistry experiments to the kids. So as you can see on the picture on the right, there is a fish and a few of us in class. We do a lot of things to just make our school experience better. And this project is kind of like a cherry on top of a cake. As our motivation, we don't have anything revolutionary to say because we didn't learn really anything about it in school. We, as many people, had a stigma about nuclear anything really. When someone says nuclear, the first thing we think about in Croatia is Krško, and in Europe it's Chernobyl. So when we dived a little in the topic, we wanted to change that. Our video, Nuclear Medicine Past, Present, Future, was like a nice interlude in the field both of us would like to work in. That might not be nuclear chemistry, nuclear physics, or anything like that, but we really like biology and chemistry, and that is something we love to explore. As we broke that stigma in our heads, it's comforting to know that our video lives on the internet, so on YouTube, and really anyone who's interested can see it. And if someone isn't interested in the subject, even a 3-minute video can be boring. So we decided to make our video as fun as possible with many giggles, transitions, and laid-back scenes. In the end, I would like to say that a few of our friends were our camera and light crew, and also a great moral support. So we are grateful for them too. And we had a lot of fun making this video, so we hope you enjoy it as much as we do.
So let's start and let's go watching this video. Emilia, please.
I will never understand why people hate on nuclear discipline so much. They don't even bother thinking about all the good sides it brought us. For example, I bet if they knew more about nuclear medicine, they would change their mind.
In 1936, there was a man who started it all, a man named Ernest Lawrence. He was a physics professor at Yale Medical School, where he took a leave of absence to visit his brother John in California in his radiology lab. John was working on treating leukemia with phosphorus-32, so it's no wonder we call him a father of nuclear medicine.
Oh, don't be so dramatic. And we can't give credit to just one physicist either. There were a number of other great scientists who contributed to the development of nuclear medicine. We can start at least a century before, in 1923, when chemist George de Hevesy discovered that a radioactive substance is chemically inseparable from the element of which is part. After, Henri Becquerel discovered mysterious rays from uranium, and Madame Marie Curie named them radioactivity.
Oh, that's for sure. Even Madame Curie's daughter, Irene Joliot-Curie, and her husband Frédéric made a great progress when discovering that aluminium foil irradiated with polonium preparation is radioactive.
I didn't know that, and there were a number of discoveries in the past 60 years. By the 1970s, most organs of the body could be visualized using nuclear medicine procedures. In the 1980s, radiopharmaceuticals were designed to use in diagnosis of heart disease, and in 2001, there were more than 25 million nuclear medicine procedures done around the globe.
Well, that's all really cool, but I don't really like history. Today, we can actually say what nuclear medicine really is. It's, of course, a medical specialty where radioactive substances are used to diagnose and treat different diseases. It's kind of like you're doing radiology inside out. Today, we have the most common diagnosis. It's scintigraphy, is used to scan your insides two-dimensional, and SPECT to scan it in 3D. Both use gamma cameras. But I always thought that radioactive rays are bad for you.
Well, these are trained specialists, so there isn't a bit of a worry. Although there needs to be predicted beneficial outcome to actually use the rays, and sometimes the patient needs to be prepared in some special ways.
And is there a future in nuclear medicine?
Of course, it's developing rapidly. We already have nuclear imaging, as you said, but in the future we might be able to understand relations between our brain and maybe our dreams or different disorders. Doctors could also have the ability to predict how a certain person would react to a treatment, all thanks to nuclear medicine.
I know why big water molecules are chasing me in my dreams.
Yeah, for sure. See, if people knew more about this, I'm sure they'd be much more at peace with this subject.
I agree, but how can we actually educate people on this subject?
Thank you for your video to the PRHG team, and great applause to you too from all the audience. And then some questions from the jury. Let's see if there are any questions.
Okay, I just want to pay compliments if I can. I pay compliments to the team because you have been actually very, very nice in setting up this video and also the presentation with a very humoristic way and also a serious commitment. And also I can say also the scenes were very nice when you throw the little bear and so on. It was very nice. I really appreciate it. Let me say it is enough clear that you are heading towards maybe a career in the future for nuclear medicine. What do you think about the nuclear energy instead for producing power, let me say, for electricity or something like that? Just a question.
Well, I think that we weren't really discovering and exploring that part of nuclear, but as we learned through this past 4 days, I think it's nuclear energy is going to be used much more in the future, and I think it's a good thing that it will be used. And we just decided that we would see how it will be used in medicine, nuclear medicine. So yeah, we didn't really discover much about nuclear in general, but I think that from all that we saw in the past 4 days, I think that nuclear energy really has a future, and it has a good future, so that much more people will understand that it's not a bad thing, and that a lot more people will start actually using it and remove the stigma.
Okay, thank you very much, and let's say best congratulations for the excellent performance in both the presentation and the video. Thank you.
Thank you very much.
So great result, attracting the interest of one of the team also to nuclear science. has been achieved by this nuclear competition. And Leon, yes, please.
So thank you very much also to this team. I'm again convinced today, once more. I would not really ask you a question directly to this team. Let me just make a generic comment, if I may. First of all, thank you to all of you. You had a very, very hard work, and you actually taught me a lot. I learned a lot of things. I have long notes, and there is one burning thing which I would like to share with you and perhaps get some feedback. So the burning one is the following. It appears that it's not very easy to find universities with nuclear subjects. My question would be, is this correct? You all had troubles to find universities? It is, by the way, I know it's like that, but I would like to have your feedback now. And what can we do that people in high schools would actually get a glimpse that there are also universities with nuclear programs around? There are not very many in Europe, by the way. It's in the order of 70 or so, not much more. And there is more than 1,000 universities in Europe, just for a feeling. Any thoughts from you?
Well, if I may say, in Croatia, we don't have a nuclear program, but I think that as we discover, we can go and kind of learn anywhere in Europe, but I know it's probably expensive for some people. So I think that it would be better if even in high schools, there were much more competitions like it was this one, where people could get introduced to the subject of nuclear energy and everything else around it. So I don't think that maybe nuclear energy in college is the best way to go, because I think people should be taught about it much earlier in life.
Great, thank you. By the way, look at the electrical engineering faculty in Zagreb and look for Professor Davor Grgic.
Well, if I may interrupt, in Bulgaria, because we have a nuclear power plant, I'm pretty sure that in Sofia University, there is such a program, indeed, and it is actually a bit popular, but I'm quite skeptical whether it is better than the programs in other countries. But we have such program for sure.
Yes, so, I think so, that there is.
For Bulgaria, probably... there is this one place in Sofia, the capital, the university, if you want. Yeah, but we have.
But I share your estimate, there is only one. Like
yes,
in Croatia, there is only one spot, a little bit hidden.
It's not hard to miss it. I mean, everyone knows about it because it's only one, but yeah, it isn't really good that there are no more.
Yeah, so Emilia just posted, I guess, the link to the list, to the possible list.
Yeah. From that link, you can click and visit the webpage from the ENS webpage, but as well also the INEN webpage. You can visit the education and training section, and there you can find all master's degree, bachelor degrees, and PhD also schools all around Europe that are providing nuclear courses in several fields, I would say. So moving from Bulgaria to UK, France, and all over Europe. So you can visit that link. I suggest you to have a look to that page, take a look at that page, and to see which are the possibilities all around Europe. So thank you all again for your presentation. We have again 2 minutes before the coffee break. So if Emilia, you want just to anticipate to introduce the next.
Mattia, can I have a quick question? I'm not sure if we lost Mattia or is it me?
I think Mattia is disappeared for a second. So Mattia, are you with us?
But I think, Papa, you can have the question.
I'll make the question to use the 2 minutes before Matia is back. So I'm gonna continue on Leon's scope to ask the question also generally to all, and of course I also add my appreciation to all of the teams for the great effort. The question I have, so I ask it first to PRHT, but also to the rest of the team. So clearly this last team showed a lot of passion for nuclear medicine. But the question I'd like to ask all of you is, it definitely is not an easy decision when coming to the end of school to choose what career path you would like to follow on, university, etc. How are you kind of finding now, or how easy is it for you to kind of get information of all the options you could have? I know it's a tough decision, but do you feel you have enough information to kind of decide with with a lot of certainty what you would like to become, or is it really challenging?
Well, if I may answer,
Sure.
it is challenging, especially to us, I would say, because like I said, we are going in a school where everything is equally, we learn about everything equally. So it's not specifically just physics, chemistry, and biology school, for example. So we have a lot of different paths we could take. So we have teachers who like to work with us, and our teacher this year brought a lot of people from different fields to tell us about their jobs and different universities. So I think that in our school, it's not that difficult because we can see what we like to do, and there are projects we can go into, and teachers are telling us about all the options that we have. But I think that other schools sometimes don't do that, and there are still a lot of people that we know that don't know what they want to do. So I think that this kind of education and bringing people from different fields would make it easier for us, because it is a big decision.
Yeah, thank you.
If we may answer as well. So in Croatia, we're going to focus on career path in nuclear physics. So in Croatia, it's learned at the very end of the last year of high school. So right before the final exams. And by that time, everyone has already made up their mind about what they want to be in life. And we do study about it, but it's very elementary. It's a very elemental part of knowledge. So we don't really get the opportunity to go into that direction unless we're sort of pushed towards that direction before by our teachers and by competitions like this one. So I'd say that would need to be worked on a little bit more.
Thank you. Very valuable comment.
So if we can go on, I'm sorry, I was frozen. It's funny to say, but when outside there are 37 degrees, but it was. So we can go for the coffee break, as said before, and we'll be back in 15 minutes. So 15:15, 3:15. We'll be back together to go on with the lectures of today's program. Thank you.
Thank you. Bye-bye.
Bye all.
time to start again our session. Most people is coming back. It seems to be more or less the same number of participants. We can stop sharing the background music. So I ask people just to reply or send something, message, or right at the end if they are ready to start with the first lecture, please. If you are present and we can start. Yes, no. Okay, Team Humphrey finish its coffee break. Laura as well is finishing her coffee break. And then any other reaction, we can wait 1 more minute. Looking for people joining us after the coffee break. Okay. So we are ready to start with the second part of today's session. We will have 2 lectures. The first of these 2 will be held by Professor Riccardo Ciolini from University of Pisa, where he's teaching physical fundamentals of nuclear engineering and radiation protection. So his presentation will be about this last topic, radiation protection. Professor Ciolini, when you're ready, you can share your screen and start your presentation. Please, the floor is yours.
Yes, thank you, Mattia. Okay. Okay. Okay, good afternoon to all of you. In this short presentation, I illustrate you which are the ionizing radiation and some basic of radiation protection. Starting from the first point is the atom, the atom composition. Particularly, the atom, as you know, is made by a central part, the nucleus, and an external part, the electrons. Here in the slide, there are represented the dimension, and also there is a picture on the right where there is a comparison between the dimension of the atom and an apple and the dimension of the apple and the heart. The identification of each atoms, each nucleus, depends by the number of protons and neutrons that compose it. And so the nucleus is made of these two particle type, proton and neutrons, which dimension are very small with respect to the entire atom. In such a way, we can say that the atom is practically empty. And in particular, in nuclear physics, not as in chemical physics, we have to identify each nuclear species by 2 numbers, not only 1 number as in chemistry. In chemistry, it's enough to specify the atomic number in the Mendeleev table, but here we have to characterize each nucleus by the number of protons and the number of neutrons, because if you change this number, the properties of the nuclear species change a lot, or can change a lot. In particular, we have the atomic number Z and the mass number A. The atomic number is the number of protons and also the number of the electrons. The mass number is the number of protons plus the number of neutrons, so the number of nucleons. And normally we write this in this way. Here we see the uranium-238, and normally we report the mass number, and knowing that the atomic number is related to the chemical symbol here. The uranium is 92. And this, depending on this A number and Z, we can represent all the possible nuclear species in a map that is the chart of the nucleus. That is for nuclear engineering, nuclear physics, as is a chart as the table of Mendeleev is for the chemical scientists and so on. This type of species can be of different types. In particular, some of them are stable, others are unstable, and this is due to their composition, to their number of nucleons. Stable means that they remain in that state situations as for an indefinite time. Unstable means that they are transformed naturally in some other radioisotopes, and these are the radioactive isotopes or radioisotopes. Then we can have another classification of the nuclear species, the natural or artificial. Natural can be found in nature, in the ground or in the earth. Artificial are man-made, produced, for example, in a nuclear reactor. This is an enlargement of one of the table of nuclides that you can find on the web. So you see there is two axes, the proton number and the neutron number. Each point, here represented by a square, identify nuclear species, and the color identify the radioactivity and the time in which it decays. You can see it later better. So radioactivity is a natural phenomena, is the transformation of some of these nuclear species in another one by the emission of some particle of some radiation. Is a phenomenon that was discovered in 1896 accidentally by Becquerel, who was making some experiment with the fluorescence of uranium. He found that the sample that he was analyzing emits some radiation, even if it was maintained in a drawer in the dark, because in the period in which he was doing the experiment in Paris, there was not sun, and he maintained this sample in the drawer for some days, but he see that it has emitted the radiation. So this means the radiation comes directly from the sample and not after the excitation of the sun. This is a natural phenomenon. There are some radioisotopes that emits radiation, transforming in other. And the radiation that are emitted are divided in three types, and following the letter of the Greek alphabet: alpha, beta, and gamma. Alpha are the first type of radiation that was discovered, are nuclei of helium-4. Beta are 2 protons and 2 neutrons. So it's a particle made by 2 protons and 2 neutrons. Beta are electrons, are like the electrons in the electronic cloud of the atom, but the name means that they comes from the nucleus. Gamma are an electromagnetic radiation, as the other electromagnetic radiation, but characterized by different energy, more energy, and the origin is directly from the nucleus. Each of these particles has a charge, so it has a different charge. Alpha has a charge equal to 2 times the charge of the electrons. Beta is equivalent to electron. Gamma has no charge, and so they can be this can be put in evidence by considering the behavior of this particle magnetic field. For example, you see the gamma is not affected by the magnetic field, and also they have different mass. In particular, the alpha is very heavy with respect to the electron, because the mass of each nucleus, protons and neutrons, is around 2,000 times the mass of each electrons. These properties depend on the nucleus of some species. So some species are radioactive, some not. And this radioactivity does not depend on the chemical form of the material. For example, if you have uranium, it's radioactive, and its radioactivity does not depend if you have uranium oxide or metallic uranium, and so on. Normally, we found in nature that when the atomic number is high, for example, higher than 84, that correspond to the polonium, we have the radioactivity. So the nucleus becomes enough big, and so it tends to decay, and the decay is a process in which the nucleus reach a lower content of energy. Each type of decay, alpha, beta, and gamma emission, is characterized by the same radioactive law, that is an exponential, decreasing exponential law, that is written here. So the radioactivity decreases with this law, with time, but the parameter that governs this is this lambda. So the velocity in which it decays, the radioactivity, the number of nuclei is reduced, depends on this lambda, that is the decay constant, or on its inverse by multiplying by the logarithm of 2, that is the half-life. The time required to reduce of a factor of 2 the number of the nuclei. So, for example, the uranium has a very, very long half-life, billions of years, but other nuclei can have seconds or minutes and so on. So the, the phenomena can vary very large as time interval. When we have very short half-life, the radioactivity after sometimes disappear, but we have to consider that a lot of radiation are emitted. Instead, if we have a very long half-life, the radioactivity lasts for a lot of times, but the emission rate is reduced. So we have to, it's not enough to characterize the radioactivity only with this law, but we have to introduce the concept of activity. That is the product of the number of nuclei and the decay constant. And this is the product lambda n, that is the variation of nuclei per unit time. So it is measured in becquerel. 1 becquerel is the same as the Hertz, is 1/seconds, means that we have 1 decay for second. 1 atom, 1 nucleus is transformed for each second. Normally, in the laboratory, for example, we have a source of kilobecquerel or sometimes megabecquerel. And if we increase the activity, we need to a particular attention and shielding and so on. This is to say that the number of nuclei that decay in a sample are in a very limited way. If you have a megabecquerel activity, that is an activity not so negligible for the laboratory, but chemically you cannot distinguish this nuclei with the other because the number is very limited. So a very low number of nuclei is enough to create some important activity. The old unit is the Curie, that is the activity of 1 gram of radium-226, and this is a high activity, is 37 gigabecquerel, is enough high activity. So together with the radiation emitted by the nucleus, there are another type of radiation that we can join to them, and they are the X-ray that were discovered one year later than the activity, and the X-ray were discovered by accelerating electrons emitted by cathode, which is heat by thermionic effect, and these electrons were accelerated and breaked by an anode. And during this process, they are electric charge that are breaking a very short time, very short interval of space. They emit this radiation, and this radiation are X-ray. This is the example of an X-ray tube, and also they were discovered by during another experiment by Röntgen, that he was studying phenomena associated with the passage of electric current in low pressure gases. He found this type of unknown radiation that was named X-ray. So the radiation that normally we speak about them, or people have fear of them, are practically the ionizing radiation, because the other radiation, for example, the mobile phone, no one of us has a fear of them because we use these devices a lot and so on. Ionizing radiation are classified by the effect that this radiation can have in matter. In particular, the name ionizing means that they can ionize an atom. Ionize means that can give energy to one of the electrons and remove the electron from the atom and make a free electron and a positive ion. So these radiation are made by the radiation emitted with the radioactivity, so corpuscular radiation, that means they have some mass, like alpha, electrons, protons, and also neutrons that are produced, for example, in nuclear reactors, but also wave radiation that are characterized by a wavelength, and they are named as photons. So they have two types, in particular the radioactivity and the X-ray. They can ionize, but can also excite. In some way, they transfer energy to matter. So this radiation has associated a certain risk because the excitation, the ionization is something that interferes with, for example, in the body, with the chemical process of the cell. But we have to consider that these radiation are part of our art, where we live. Here, for the distinction between ionizing and not ionizing is not so net, but normally we consider the ionizing radiation the radiation that has enough energy to remove an electron from the hydrogen. So alpha particle, beta, and protons and neutrons all are ionizing. Some misunderstandings can occur in for the photons. Gamma and X are surely ionizing. For the ultraviolet, the high energy part, the ultraviolet radiation can be ionizing. It depends also on the atom, because the ionization energy depends a little on the atom. All the other radiation, the non-ionizing radiation for communication, infrared, and so on, are characterized by less energy, and so the energy is not enough to remove the electron. So normally the behavior of this type of radiation with matter is different. But as you know probably, we live in a world where the radiation are existing. So if you take a sample of soil, for example, you can find very easily uranium, thorium, and also in our body we can have some radioactive material, for example, the potassium-40. This diagram, we can see the radiation that we receive normally in our life. We have a natural contribution that is made by radon. Radon is a gas that is a daughter of the uranium, and is the buildings and also the environment, and we inhalate it, and so it have a dose to the lungs. Cosmic radiation that arrive from the sun, also the galaxy and so on, and then from the ingestion of food and drink water. Then there are other terms that comes from the industrial activities, but mostly by the medical diagnosis. For example, the computer the CT of the body, X-ray. So a lot of these treatments are give a dose, increase the level of the dose. The level is estimated, it's an average level, as 3 millisievert for year. This unit is a unit that measures the quantity of energy that is received by the body. And for the moment, we take, as we see later, how it is defined. So this constitutes the natural background of radioactivity. So we live in a radioactive world, and the radioactivity varies a lot from site to site. In some places, there can be also 10 or 20 or 50 times the level of background that we can find in other places. This radiation is part of our body, so we have not to have fear of them. The natural radioactivity in particular can be divided in 3 types, depending on all the nuclear radioactivity that we found belongs to 3 families, we can say. Each family has a parent, as a first daughter, that can be the uranium-238 or 235, and then there are the chain of the thorium. There is another chain, the uranium-237, the Neptunium-237, but normally we don't find in the nature, because these are characterized by a half-life of the parent that is less than the age of the Earth. So this uranium-238 has a half-life that is longer than of the order of the age of the Earth, and so we can find now some of it and all its daughter in the soil and so on. The uranium-235 is contained in less percentage because it has a shorter half-life. And also knowing the quantity of 38 and 35 in uranium, we can also induce and calculate with a large approximation the age of the Earth. Radon is a gas that is the daughter of the radium, that's daughter of thorium 30 and so on, and this is diffused in soil and also in the environment, and is also something that we have to measure, for example, in buildings, because the level of it cannot be over some certain value. There are examples of some activity in some soil. Granite, for example, are characterized by a lot of higher activity, and some sands, zirconium sands, that are used, for example, in some ovens and so on. And also some foods, for example, the bananas has a lot of potassium, and also potassium-40. So this is only to show that radioactivity is part of our world, and so radiation has not that fear of them, because they have a lot of applications, from production of energy, from therapy, for example, to treat tumors that are not otherwise, it's not otherwise possible to treat, but also for industrial applications, sterilization and so on. A lot of foods are sterilized by the using of very intense gamma field. So now I show very easily how the radiation interact with us. They are ionized radiation, so not to fear them, but we have not to use them as they are not, they have no damage, no effect, because due to the fact that they ionize, they can interact with our body and produce some variation in the chemistry of the body. The interaction can be of the external type, the source is outside the body, or internal type, if we inhalate, for example, radon gas and the daughter of radon, the source, the radioactive source, enter in the body. So this, and then when it is inside, we have to see also how it is released from the body, it follows the process of it. The radiation are characterized by different penetration. Particular alpha and beta are not important when, or we can say not so important when the radiation is a form external type, because alpha are normally stopped by a paper sheet, normally if the energy is emitted from radioactive source in the laboratory. Beta normally are shielded by a little thickness of plastic. For shielding process are the most important, the gamma and the neutrons, because they need higher thickness of material to be shielded. But alpha and beta are important when they enter in the body, because they they travel a very short distance and they deposit the energy in this very short distance. So alpha and beta are not important outside, but they're more important than the other when the source is inside the body. Which is the mechanism of damage of this radiation? The radiation has some energy associated, so the energy, when the radiation hit, for example, the body, they deliver their energy in some way to the body. So at the end, we can say that all this energy is transformed into heat. But to heat the body of 1 degree Celsius, we need an energy of 4 kilojoules per kilograms of radiation. This energy increases the heat of the body of 1 degree Celsius. But we know that this value of the energy is 1,000 times the energy that is lethal for man. And for man, normally is lethal. This 4 gray is joule per kilogram. This is normally enough to kill a man. So this means that the effect of the radiation is not related to the heating, but is related to the disruption of chemical bonds. In particular, is related to the effect on the DNA. The radiation, the ionization of the radiation can divide the DNA in one or both the strand. And if, for example, we have an interruption here, then knowing the other part of the DNA, our body can reproduce correctly the DNA. But if we divide the DNA into two parts and we have a double strand break, then it is more difficult for the cell to reproduce correctly the DNA, and in some cases it can reproduce in a wrong way, in such a way the reproduction of the cell is not correct, and this produce cancer or tumor, or can produce in this case. But we have to consider that this effect depends on the radiation. For example, here we see the electron interact here, here, and here. The alpha makes a lot of interaction. So the electron has a lower probability to break in two parts the DNA than the alpha, because it has a very large distance between one interaction and the other. And so the energy that is lost by the electron for unit distance is less than the alpha. So from here we understand that not all the radiation has the same effect. From this point of view, the alpha are worse than the electron, considering the same energy that is deposited, but if we have an alpha, the effect can be also 20 times than the electron. But it's important, I want you to consider this number, that for each day, we have in our DNA this number, 10 to 14th, of this strand break in our DNA due to natural radiation, and this variation are normally fixed by our repair mechanism of our body. So we have a lot of this interaction, but our body is, we can say, to live with this background. So this is the process in which the interaction can produce the effects. And the effect of the radiation are of type. We can start with the DNA damage. The DNA damage can induce the death of the cell or DNA mutation. In particular, we can have two different types of effects. Effects in the irradiated body and or in the offspring, somatic and effects, but more important, deterministic and stochastics. The deterministic effects occur only when the dose, so the energy for unit mass, is higher than a certain value. So, for example, 0.25 gray, that means 0.25 joule per kilogram, can be a threshold over which we can have some of these effects. For example, effects on the length of the eye and so on. If we stay below this value of the energy, the effects are not obtained. But we can have the more important from the radiation point of view is the stochastic effects, because these effects are probabilistic effect. They can occur or not, and there is not a threshold. So, or better, we assume that there is no threshold for this effect. So this means that each irradiation, even if the dose is very low, can has a risk that is not zero. And normally this is the philosophy that we assume in radiation protection. So here there are description of this effect. Because not so much time, and only to show you the below 0.5 gray, practically have no effect in no among people, but over 3.5 gray, this is the lethal dose in 50% of the people after 30 days of irradiation. The radiation protection is involved only in the protection from the stochastic effects. Each radiation has a risk, very low, and so we can assume which is the maximum value of the risk that we can sustain. In particular, we assume that the radiation and the response and the risk is linear. We have data at very high value of the radiation dose, for example, from the survivors of the atomic bomb, and we extrapolate this data to the very low value of dose. We have to say that when there is a disease like a tumor or a cancer, it's difficult to identify the cause and to associate it to the irradiation, to the dose, because a lot of factors, chemical factors, food, and so on, can induce this cancer. In particular, we assume a risk that, from a radiation protection point of view, 10,000 people, if receive a dose of 10 millisievert, the risk is 4 cancer deaths. But you have to compare this with the 2,200 normally value of the tumors expected in that population for all the other risks. So this is the definition of the dose. Now there's not so much time. So, but it's the energy released for unit mass. Consider the radiation of the body, and this is a gray, the unit of it, joule per kilogram. Then we have to multiply this value for a coefficient that depends on the radiation, because each, as we have seen before, the alpha has a higher effect because the deposit energy in a very shorter way than the electron. And then we have to multiply for another term that considers the organ that is irradiated. To irradiate the hand is not the same as irradiate the lung or the breast or gonads for people. So normally we obtain the gray for these two coefficients, weight, radiation, and type of the body, in the type of part irradiated, and we obtain the sievert. So normally the dose is reported in sievert and millisievert and so on. So to conclude, radiation protection is the protection from the radiation, but we avoid the objective is to avoid the deterministic effect, and to reduce the probability of stochastic effect to the risk of stochastic effect to a value that is acceptable for other industry. For example, in other conventional industry, we assume that there is a risk to die that is not zero, and we assume that this risk will be the same for nuclear, assuming the safer conventional industry as a reference. Radiation protection is based on three principles that are the justification, optimization, and limitation. Justification means that we can use ionizing radiation only if it is necessary and if the benefit is higher than the risk, because there is a risk that cannot be excluded. If this is justified, activity must be optimized, so we have to reduce the risk as much as possible, considering also the economical factor, but at the end we have also to limit the value of the dose to a value that cannot be overcome, because we have to stay far from the deterministic effect. And also to inform you that there are a law that regulates the radiation protection. There is the directive, the European directive, that each member of the European Union has to transpose in internal law. And this is to protect people that use ionizing radiation for work, and also to protect the population from the effect, and also from the now in the new version of the directive, from the protection for the naturally occurring radioactive materials, so materials that are used in the industry but are of natural origin, but they contain a lot of radioactivity. Okay, so I finished. Sorry for a little longer.
So thank you, Professor Ciolini, for your thorough and detailed presentation on radiation protection. So now, if there are any questions from participants, you can write in the chat or raise up your hand, and please open your microphone, and you can ask the professor whatever you're interested in about his presentation. I cannot see the audience still. Any question?
No question. Okay, all is okay. Okay, better.
Not yet. I have a question for you, Professor. So, how do you think, Lee, there are, like in general for nuclear, a misperception of what radioactivity is? Usually it's directly linked to nuclear power plants, as nuclear energy is sometimes wrongly directly linked to Chernobyl accident, for example. So, but indeed, radioactivity is all around us because it's in the nature. So maybe it could be a solution to stress this point, to also to show, as you did, for example, some clear example. Sometimes also using in our communication the concept of the nuclear banana as a food. Common food that contains radioactivity, radiation because of potassium, or many other. I saw recently a video explaining that in some part of Italy, above all central Italy, for example, in Orvieto, a wonderful medieval city built in the tuff, and tuff absorb radon, if I'm right. So, and there the average radioactivity on a year is higher than in some zone of Chernobyl, for example. So maybe could be this a solution to be kind of mythbusters of all this misperception around radiation and radioactivity.
Yes, the solution I think is the more information, and but it's not easy, because I also experiment in my family. My father, for example, has a fear of radiation. Also, I think it's a necessity to inform and to report the data. For example, also to show that some materials that we think are radioactive are natural, and we can find it. So is, but I think is necessary, because the radiation at the end we don't see it, so it's difficult to compare this to something. And so it's also the better is to be, for example, take a sample, measure, and compare with other. But it's not easy because some people does not have something to do with radiation because they have fear by principle, we can say. So I think, but in the next generation, I see is more more comprehension, more because, for example, now there are a lot of information also in the web. People can see, respect to 20 years ago, where is more the information are less diffuse. I don't know if I answered to the question. Okay.
Yeah, thank you.
Thank you.
So if there are any other questions from the audience, and say thank you to Professor Cellini for his interesting presentation, and we can move to the second lecture. So now we will see how radiation protection works in practice. So we will start watching a video recorded by Martin Laroche, and then Professor Tila Pesniak, professor at the Budapest University of Technology and Economics and INEN Vice President, will be able to answer to your questions here live after the video. So Emilia, if you're ready, we can start with the video.
Dear ladies and gentlemen, my name is Máté Lajos, I am physicist, and I would like to present you decontamination today. As beginning, I have to share you some basic information in connection to decontamination and some definition as well, in order to clarify the meaning and share a good practice. In the framework of radiation protection, the contamination always means contamination with radioactive substances, radioactive materials. What can be contaminated? Everything. Tables, skin, even radioactive materials, or radioactive material containing devices and dose rate meters also. We call the situation surface contamination, and the use unit for characterizing that is the becquerel per square meter for a given radionuclide. Sometimes we only measure CPS, which is the abbreviation of count per second, or CPM, count per minute. Step a little bit further from the topic and have a look at the type of exposures. If you are affected to ionizing radiation, it can be external and internal exposure. Start with external radiation. We make differences between alpha, beta, and gamma radiation based on their range, free path lengths in the air. The most dangerous are neutron and photon radiation, X-ray gammas, because they have no electric charge, so they affect several meters away. Beta particles' free path length in the air is less than 1 meter, energy depending, and the less dangerous is alpha particle, because it attenuates in some centimeter in the air. The protection from external ionizing radiation has 3 main forms. They are time protection, distance protection, and application of shielding materials. The less time you spend near the source, the less dose you receive. The greater distance you keep from the source, the less dose you receive, and using appropriate shielding material, you will be less exposed. Using appropriate material for shielding is important. The used shielding material depends on the type and energy of the radiation. For example, lead shielding materials with high atomic number shields gamma and X-ray effective. Beta particles can be stopped by a layer of plastic. Alpha particles can be stopped by a sheet of paper or even by your skin. Radiation exposure occurs when all or part of the body absorbs penetrating ionizing radiation from an external radiation source. Exposure from an external source stops when a person leaves the area of the source is shielded completely, or the process causing exposure ceases. An individual exposed only to an external source of radiation is not radioactive or contaminated and may be approached without risk, just like after a chest X-ray or CT scan. Radiation from external exposure alone is either absorbed without the body becoming radioactive, or it can pass through the body completely. Therefore, if a person is scanned with a radiation survey monitor after external exposure alone, the device will not register radiation above the background level. Internal radiation is caused by radioactive material in human body, which takes part in metabolic processes. Radioactive contamination, mainly internal radioactive contamination, can cause internal radiation. Let us speak about radioactive contamination. Contamination results when a radioisotope, as gas, liquid, or solid, is released to the environment and then ingested, inhaled, or deposited on the body surface or on any surface. We have to make difference between external and internal contamination. First, external contamination. External contamination results when radioactive material is deposited on skin, hair, eyes, or other external structures, much like mud or dust. External contamination stops when the material is removed by shedding contaminated clothes and completely washing off the contamination. How to diagnose? We have to scan the suspicious surface with appropriate radiation survey meter. We have to apply shielding against the spreading radioactive material, for example, stay in closed place in a house, or wearing whole body covering protective clothes, gloves, and so on. Shielding blocks radioactive material from covering the entire person. Make it clear, we protect ourselves not against ionizing radiation, only against radioactive materials depositing on our skin or clothes. So, what is internal contamination? Radiation exposure also occurs after internal contamination, for example, when a radionuclide is ingested, inhaled, or absorbed into the bloodstream. Have a look at the internal contamination via respiratory tract. When aerosol particles are inhaled, smaller particles can reach the alveoli, whereas larger particles will remain in proximal airways. Tiny particles can be absorbed by the lymphatic system or the bloodstream, or continue to irradiate locally until exhaled, removed, or depleted of their radioactivity. Have a look at the internal contamination via digestive tract. If swallowed, soluble radionuclides may be absorbed in the upper tract, whereas insoluble radioactive particles may affect the lower gastrointestinal tract. Depending on the specific radioisotope, particles in the gastrointestinal tract may be lavaged, expelled, or removed using drugs. Last one is called decorporation. Have a look at the internal contamination via radioactive dust in open wounds. Smaller radioactive particles in open wounds may be absorbed into the body via blood or lymphatic channels. This kind of exposure stops only if the radionuclide is totally eliminated from the body with or without treatment. As a summary, internal contamination results when radioactive materials is taken into the body via inhalation or ingestion or open wounds. Internal deposition of radioisotopes in organs results in local exposure at that location. Internal contamination continues until the radioactive material decays, is flushed from the body by natural processes, or is removed by medical countermeasures. How to diagnose? If after external decontamination, an appropriate radiation survey meter continues to identify significant residual radioactivity, suspect internal contamination. Collect spot urine sample from isotope measurements. Make instructions for sample collection, labeling, packaging, and shipping. Consider total body radiation survey with modified hospital nuclear medicine equipment or with whole body counter. If the contaminating radionuclide has no measurable gamma radiation, the whole-body counter, high-purity germanium detector, cannot detect the radiation. Measurement of urine, blood, excretories have to be analyzed then. Have a look at the incorporation. After inhalation, ingestion, or wound contamination, small radioisotope particles may be transported via blood or lymphatic into cells, tissues, and organs. Isotopes can be alpha, beta, or gamma emitting radionuclides. Most dangerous are alpha emitting radionuclides because they transfer all of their energy to the nearest tissues. Radioisotopes can be incorporated into one or more organs specific for that chemical element, for example, thyroid, lungs, kidneys, bones, and so on, resulting exposure at that site. Medical countermeasures called decorporation agents or other procedures, for example, diuresis, may be needed to remove radioisotopes that have been incorporated into tissues. Toxic effects of radioisotopes may be due to their chemical and radiological properties. Decorporation is also a toxic effect because decorporating drugs are not specific for the radionuclide, but specific for the chemical element, and usually the chemical elements with similar electron field. What to do in case of an emergency? Don't panic. First step is life-saving, first aid, so giving help to the sick or injured person until full medical treatment is available. Once we are convinced that the person is alive and not in danger of death, we can start with radiation protection issues. In this situation, my colleague, Mr. David Mihai, helps us to illustrate an accident happened in an isotope laboratory. I prepared with some demonstrating tools, a special liquid emitting UV photons, and a handhold detector which detects these UV photons, similar to a surface contamination measuring instrument. We are wearing whole body covering working clothes, gloves, mask, helmet on the head against spatter of radioactive material. Let me introduce my colleague David Mihai, who helps us to illustrate this accident in an isotope laboratory. Welcome, David.
Hi, everyone.
David will wear this artificial wand. He was working in an isotope laboratory with well-measurable beta emitter radionuclide when an accident happened. David is wearing whole body covering working clothes, gloves. Suppose that he is wearing mask and helmet on the head against spatter of radioactive material. He is wearing personal dosimeter. He alone cannot prevent the accident, cannot make the decontamination, so we need a second person who does it. What happened, David?
I was working with strontium-90 isotope when I fell and injured. Not only my gloves, but also my skin was injured.
Now I'm making the open wound visible. Imitating the surface contamination, we use this special liquid as a radioactive material. Of course, it is not radioactive, only emits UV photons. We have a measurement device belonging to that liquid. It measures count per second and have audible beep signal. The sensitive detecting surface is covered with a thin, replaceable plastic layer in order to prevent the device against contamination. Now I am contaminating David's wound, and we will decontaminate using our prepared decontamination kit. Now it is visible, yellow liquid. It is a lucky situation, but radioactive materials not usually visible. Start the checking of the injured person. David is not in danger of death. We can communicate with him. We see his bleeding wound, but do not start to decontaminate that, because we have to check previously whether he inhaled or swallowed the radioactive material. He did not incorporate via this tract because he was wearing protective tools. Now we can carry on with the open bond. Using our counter, we establish external radioactive contamination. We have to prevent or reduce internal contamination. I remove his gloves. Now I became also potentially contaminated. I start washing his wound with physiological saline. We collect the washing liquid and radioactive waste in order to estimate the amount of the incorporated radioactive material. We know the amount in becquerel of the used radioactive material. We collect and measure the rest, and the subtraction is assumed as incorporated. We are washing and pressing the wound area. Thus, we try to remove the potentially contaminated blood from the nearest tissues. When we finished, we check the radioactivity on the wound with our counter. Hopefully, we measure less counts per second, and we have to carry out a control measurement on the tray. The most radioactivity was washed out and collected on the tray. After the radioactive substance is removed from the open wound, we check the whole body, mainly gloves, and the undersurface of the person's shoes. Thank you for your attention.
Thank you for your attention.
So as we saw how radiation protection works in practice and what to do, which steps are needed to ensure the health and the safety in the case of a radioactive accident in a laboratory, for example, with thanks to the demonstration. So now we are with Professor Krila Pesniak, that she is able to answer to your question related to this last lecture. So please, if you have any question, you can raise up your hands again or write to the chat and ask her whatever you want related to radiation protection.
Yeah.
Are there any question? Yes, we received one question. Can an external contamination become an internal one? MNP team asks.
Yes, sometimes can happen. Sometimes can happen, but it's very real. Most cases, the external contamination is on the body. If you have some injuring in the bone, in this case, it can be internal, or if you can eat something but is external contaminated, some fruits or some food, in this case, it can be incorporated inside.
Okay, thank you. Any other question? Participants. So I have a question. Okay, no, there is one question from Tim Humphrey. How quick would be the expansion of radiation in the body in the case of an internal contamination?
It depends on activity, always. If you have a radioactive source with a high activity, it is the most danger. If the activity is less and less, depends on, is it only radioactive or it has some special chemical component that is danger for the chemical side on the body. And also for maybe it depends on the how to say, which energy we have, or it depends that is it alpha, beta, or gamma source. Because the alpha is very, very dangerous, there is a lot of interaction. If the beta is it less, and for the gamma it take more time. But mostly it's also very important, the activity.
Okay, thank you. Then if we have other questions from the team. No other question?
Which is worse, for if you have an internal radiation, then it's always the worst is alpha. The alpha is the worst because it's most active. After that, the beta, and for the internal is a gamma for the long time. If it's the activity very high, then the gamma can be also dangerous. But we always say that the alpha is the dangerous. It is the worst.
Thank you, Professor, for your answers. Any other question before the next coffee break and the last part of our session? I don't see additional questions. So if there are no other questions, Emilia, thank you. First of all, thank you for Professor Stilla Peșniak and to Mate Lajos for the demonstration in the laboratory about the radiation protection. Thank you very much. And then now we have a few minutes. We can anticipate, we can introduce you a bit what will be the program for the next day, the last day of the nuclear competition. Please, Emilia, if you want to introduce it.
Yes, hello everyone. Yes, so just for tomorrow, we will have 3 sessions within the roundtables. The first session is with the first session will be with the teachers. So I got already confirmations from 3 teachers. It's David Teferer, Vladislava Viktorova, and Marlena Cukteras. 3 teachers will be telling you the stories of their experience, e-learning during the pandemic situation, and also giving the feedback of the competition of this week. Further, we have 20-minute session, Ask Me Anything session with our VIP. Our VIP is tomorrow Valérie Foudon, Director General of French Nuclear Energy Association. And so I shared with you her CV, so please prepare the questions for her on her career. And afterwards, we will have a session where we would like to invite all of you to actively participate, to ask you about your feedback, about your impressions of this competition, what it could be improved, what was not best done, what are your highlights of this week. And I wanted to have a team of 5 students. I asked them to confirm. I'm still waiting for confirmation. So those students who received the invitation for the roundtable tomorrow, please confirm. And yeah, I'm very excited to have you tomorrow at the roundtable. I will moderate it. So yeah, if you would still like to participate, I will ask you anyway a lot of questions via polls. And we also share today with you our survey to ask you for the feedback on this competition, so we can really improve our service and make it better next time, for example. Okay, so that's it from my side, and see you tomorrow.
Thank you, Emilia. So I think we can go for the last coffee break. We have again 15 minutes coffee break, and then we will be back together for the last part of today's session at 4:30. Thank you. See you later. So here we are again for the last part of today's session. I hope you had some rest and you're ready to restart this last part that is waiting us. I don't know if you are ready and there, ready to follow. Just tell me yes or send some signs. Yes, Laura is ready. Great. And also Nicolce, great. Nicolce team. And I ask to the next speaker, Bence Biro, if he's ready as well.
Yes, I am ready. Hello, everyone.
Hello, Bence. So if you want, just waiting for the people to come back, to try to share your screen and your presentation and check if everything is working.
Yes, of course.
Okay.
Can you see my slides?
So yes.
Yes, perfect.
You can
Thank
probably see it, and everything seems to be okay. So a short introduction before your presentation focused on nuclear energy specialization, on nuclear energy, pardon. Bence Biro is an energy engineering master student at the Budapest University of Technology and Economics with a specialization in nuclear energy. And moreover, currently, Bence is working on a power market simulator and demonstrator tasks at the BME Institute of Nuclear Techniques, if I'm right. So, yes, Bence, the floor is yours. You can start whenever you want.
Thank you very much. Hello, everyone. I welcome you to my presentation, and thank you for the presentation and the opportunity to be here. My name is Bence Biro, and I'm here to talk about nuclear energy and how nuclear reactors work. I would like to start my presentation with some Hungarian aspects in nuclear history. Hungarian-American physicists Teller and Szilárd Leo are the big minds behind nuclear fission. Both of them emigrated because of the war to the United States. Szilárd Leo conceived the nuclear chain reaction in 1933 and worked out the idea of nuclear fission reactor in 1934. And he was also part of the Manhattan Project. And Teller was called and is called the father of the hydrogen bomb. And he also worked in the Manhattan Project. This Manhattan Project was a code name actually for an American-led effort to develop a functional atomic weapon during the World War II. There are some funny stories about the Hungarian scientists because with each other they always spoke the Hungarian language, and the other scientists didn't actually understand them. And there are some rumors that the others sometimes even thought they are some kind of UFOs when the two Hungarian scientists talked science in Hungarian. So I believe it's a really interesting Hungarian aspect. And next, I would like to give you some insight to the nuclear industry through numbers. As you can see, there are currently 443 operating reactors, so approximately 450, and they have a combined of 395,000 megawatt installed capacity. These 450 reactors provide 11% of the world electricity, and they actually do it in a green way without emitting any greenhouse gases to the atmosphere, which is really important nowadays. It's a well-spoken topic. And as you can see, there are 55 new reactors under construction in 2021. It is also necessary to identify the countries with the most nuclear reactors. As you can see, the United States is leading by a milestone, and they are followed by France and China. China is heavily invested in nuclear energy, and they are building a lot of new reactors because of the country's growing energy demand. So this number, the number of nuclear reactors and the combined installed capacity in China is going to grow a lot in the coming years. You can see also on the list Japan, Russia, South Korea, Canada, Ukraine, the United Kingdom, and also Germany. Germany is an interesting country as well because they have decided to shut down all their nuclear reactors, which is called a nuclear phase out. I'm personally really interested to see how this will play out and how Germany will manage its electricity demand without nuclear reactors. But this is a topic for the future. Before we talk about how nuclear reactors work, I wanted to show you the different type of reactors. We are going to talk about the first three types in more depth, which are mainly second and third generation reactors. But as you can see, there are a lot of fourth generation reactor concepts in planning. These are the reactors for the future. For the coming 10, 20, 30, 50 years. And there is also a somewhat new type of reactor model in the planning, and it is nearly in the construction phase. They are called small modular reactors, and they actually really excite my energy engineer heart because they can provide a much needed flexibility to the electricity system. And they do it without emitting the almighty CO2 to the atmosphere. They can do that because these reactors will be smaller size, so 50 to 200 megawatts. And they can also be used to generate electricity, heat, and also even hydrogen. So they are really exciting new reactors. But ultimately, we can say that our reactors are just big water heater machines. And they have a lot of similarities, and they have some differences as well. So now let's talk a little science, more precisely about fission. So nuclear fission is a reaction in which the nucleus of an atom splits into two or more smaller nuclei. As you can see in the picture, there is only one fissile material in nature, and that is called uranium. When a nucleus of uranium collides with a neutron, as you can see here, it splits and produces fission products, and it usually produces 2 or 3 more neutrons. It is actually 2.4 on average. And these neutrons will then cause further fissions. And a series of successive fissions is called a chain reaction. And it is also important to highlight that reactors use enriched uranium. It means that the percent compensation of uranium-235 isotope has been increased through the process of isotope separation. This process is needed because the isotope this isotope makes up only 0.72% of natural uranium. And only this uranium isotope is able to fissile and be able to sustain a chain reaction. So next, I would like to describe how a nuclear reactor works very briefly, and explain it through a pressurized water reactor's schematic figure. So a nuclear power station is basically a factory that converts the energy of the atom into a flow of electron, which is commonly called electricity. In the nuclear reactors, the enriched uranium is processed into little ceramic pellets. And it's very interesting that the energy from 8 pellets can power an average house for almost a year. So they contain a lot of energy. These fuel pellets are then sealed into metal tubes, which are then welded together to form a fuel bundle. As you can see here, this red tubes are this where were I? Are these fuel bundles, and several thousand fuel bundles are then inserted into a large tank, which is the reactor vessel, which you can see here. The nuclear generating stations split the uranium atoms, as we talked about earlier, in the fuel, and the result is a release of a tremendous amount of heat. To unlock the heat energy in the uranium, you need what's called a moderator. The moderator surrounds the fuel bundles and slows down the neutrons, so they are more likely to hit and split the uranium atoms. Here you can see the moderator in blue, because in a pressurized water reactor, the moderator is actually water. So a chain reaction of atom splitting ensures that there is a constant source of energy to heat the water. And then this heated water is pumped through the reactor in a closed system to basically a boiler. We call it a steam generator. And then this primary water heats another water, a secondary water, into high pressure steam. The primary water is actually on high pressure, and it does not boil because of that. And the secondary water is on much lower pressure, so that it can boil, which is really important in this process. And then the primary water is recirculated back to the reactor to pick up more heat and actually cool the fuel. Then what happens with the high pressure steam? The high pressure steam is pumped through pipes to a large turbine. And here it pushes the blades and turns a shaft connected to the rotor in the generator, causing the rotor to spin. The spinning rotor is a large electromagnet that produces a rotating magnetic field. And this field moves across coils of copper wire in the generator stator. And this produces electricity that could be sent across transmission lines. And then everybody can use it. So we can be part of web meetings, or we can use our lights, or actually use our air conditioning, as I am doing, because it's really hot in Budapest. And the last part, the steam coming out of the turbine is condensed back into the water using cooling water, for example, from a river, so from the outside world, and it is pumped back to the boiler or the steam generator to continue this process. So this is how briefly a nuclear reactor works. And let's talk about pressurized water reactors in more depth. So the PVRs, as you can call them, constitute the large majority of the world's nuclear power plants, approximately 70%. They have a primer and a secondary design with only the steam generator connecting the two circuits. and it is really optimal because of safety reasons. And they are actually called pressurized because the water in the primer circle is at high pressure, allowing that the water does not boil in the circle, as we have talked about it previously. So let's talk about another reactor type. This is the boiling water reactor. It's actually the second most common type of electricity generation nuclear reactor after the pressurized water reactor. The main difference between the two reactor designs is that in a boiling water reactor, there is no primer and secondary circle. The reactor core actually heats the water and turns the water into steam. So the water in the reactor core is not at a high pressure as in the pressurized water reactor. And this steam is directly going into the steam turbine. And as you can see, with this design, we have to have containment for the whole reactor, not just for the primary circle with the pressurized water reactor, which costs a lot more money, and it is actually makes the engineering people who work with the turbines and the condensator much harder because they have to deal with the radioactivity as well. This is the third one we are going to talk about. It is a Canadian pressurized heavy water reactor designed to generate electric power. It uses heavy water as a moderator. So this means that it can use natural uranium instead of enriched uranium, which is a very big difference from the previous reactor designs. And the reactor vessel is actually pierced with 100 of tubes. And these tubes contain the fuel rods. So these fuel rods can be accessed separately. And this allows us to change the fuel rods during operation, which is not possible with the previous two designs. Here in this reactor, the reactor vessel does not need to be pressure tight, so it does not, because the moderator is under high pressure only in the pipes. And because of the low pressure and temperature, much simpler sensors can be used to monitor this reactor's process. Lastly, I would like to talk to you about safety, which is a very big topic in nuclear energy. There are 3 basic safety conditions that must be met at every nuclear reactor. We have to effectively control the nuclear chain reaction. We must find a way to properly transport the energy or the heat that is produced. And we have to prevent the escape of radioactive materials. And this is a well discussed theme in nuclear energy. There are a lot of people who just work on these topics, and these safety functions are implemented in reactors by so-called deep protection. And there is a system of barriers that ensure that the radioactive material cannot be released into the environment in an event of the accident. And this barrier system actually consists of the fuel pellet, the fuel cladding, which includes the fuel pellet, the main primary circuit, for example, the pressure vessel, and the containment that is around the the reactor and the primary circuit, for example, in the pressurized water reactor. That was all I wanted to say. Thank you very much for your time. And if anyone has a question, I'm happy to answer them, or I try to answer them.
Thank you, Bence, for your presentation. Very interesting and thorough as well. It gave a great overview in a very more complex topic such as that of the nuclear energy and nuclear reactors. So if there are any questions from the audience, from the participants, please feel free. Okay, we already have one from Petco. The young scientist called Taylor Wilson, based in US, proposed a new design of a molten salt reactor. Are you familiar with it? And if yes, what is your opinion on it?
Can you actually repeat the question? I couldn't hear it properly.
Sure, I think you can also find it in the chat. So Petco says there is a young scientist called Taylor Wilson based in the US, and he proposed a new design of a molten salt reactor. Are you familiar with it? And if yes, what is your opinion on it?
I haven't actually heard a scientist named Taylor Wilson, but I have heard about molten salt reactor types. They are one of the 4th generation reactors. So I have actually have them on my slides. I'm not really familiar with them because I'm actually working with pressurized water reactors. So my field doesn't require to work with the 4th generation reactors, and in my studies I haven't actually jumped deep into the 4th generation reactors because I do believe that the 3rd generation reactors have a lot of problems to be solved, and yeah. But in the future, I would like to get familiar with them because they are the future, and we have to know a lot of them and know a lot about them actually.
So thank you, Bence. Thank you, Petco, for your question. Then, if there are any other question, please raise up your hands or write in the chat. If you have any curiosity. From MNP team, which is the best reactor between the ones you explained?
I believe it's the pressurized water reactor. It's no secret that 70% of the world's reactors are this type, and both for the primary and the secondary circuit design, it is very optimal for safety reasons, and yeah, I think it's the best one. But I do believe that the small modular reactors, which are coming, I hope, in the next years, are going to change the game in nuclear energy, because the electricity systems have to deal with the increasing number of renewable energy, and we need the flexibility, and these small modular reactors can provide this, and also they can produce hydrogen, which is going to be the fuel of the future. So I'm really excited about SMRs, but for right now, pressurized water reactors is the way to go, and they are the ones that are being built.
Okay, thank you, Bence. Any other question? You already replied to about the SMR reactors. I wanted to ask you, what's your opinion, if you have any? I saw a very positive approach and perspective you see for the future. Yes. So I was asking you if there are a lot of position paper studies on it and on the impact of the SMRs in the future of also the energy market. So, but you have a very positive approach. So you already replied me. Thank you. And any other questions from the audience? We have still time for one question, if you want. If not, we can say thank you to Bence Biro for his presentation. And I'm now inviting you to taking part to the last quiz we'll have in this nuclear competition. So now I'm going to send you the link to join as usual. Now you know better than me how to do it. So I'm going to share with you the link for the quiz. Here we are. You should have received it. So as usual, register to the quiz following the link. One participant per team or device, and please rename the avatar as you already did with the team's name. You'll have 12 questions in 30 seconds for each reply to each to answer, and then you'll get points both for correct answer and speed. I want just to remind you that this quiz will be very important because the final ranking seems to be very balanced. So today's answers will make the difference. I'm going to share the screen just 1 second, and then when all we are ready, we can start. Okay, share sound, video clip, and here we are. Now you should see my screen. Okay. And start the presentation and waiting for teams to join. Okay, you already, 16 teams. You already demonstrated your speed in your first answers. I'm not surprised. Thank you. And only one team is missing. If I'm right, we can wait a bit. There will be all closed answers as usual. You'll have 30 seconds for each question, and then maybe 10 additional seconds for the last one, which will be a bit longer than usual. So all 30 seconds for each question, except for the last one when you'll have 40 seconds. Let's wait again for the last team to join us. I cannot see who is missing.
I'm sorry, but the quality of the presentation is very bad. Can you change it?
I can try, but it's not depending on me, unfortunately. I can ask from the full screen, but I think it will not improve the quality of the streaming. I'm sorry, but it's not depending on me. So one team left right now. And then
okay, thank you.
I'm sorry, really. Okay, now we have 17 teams, and I think we are ready to start. Let's count down for the first question. Nowadays, how many percent of the world's electricity is produced from nuclear energy? 2%, 5%, 11%, or 13%? We discussed this topic today several times. Very close. Everyone has voted, and let's see. Yes, the correct answer was 11%. Congratulations. Let's move to the second question. How many nuclear power reactors operate in the world according to the presentation we saw today? 350, 450, 500, or 1,000? One team is missing. Yeah, everyone has voted. You are very fast today. Congratulations. And yes, the correct answer was 450 nuclear power reactors operating today. Next question, let's start the countdown. What is the correct order in energy producing with nuclear power plant? So steam into the core, then turbine, then generator. Steam into the core, then generator, then turbine. Hot water, then turbine, then generator. Or hot water, then generator, then turbine. 10 seconds to answer. Okay, everyone has voted. And the correct was the first one, steam in the core, then the turbine, and then to the generator. Let's see the fourth question. What is the fuel of a light water reactor? So, light water, heavy water, uranium-235 or uranium-238. Okay, everyone has voted, and yes, the correct answer is uranium-235. Let's move. We are out of the quiz. Fifth question. So, how many uranium pellets can make enough power for a house for a year? 8 pellets, 1 pellet, 100 pellets, 800 pellets. Challenging quiz today. To say that it will decide the winner, the final winner for this year nuclear competition. For the quiz section, everyone has voted, and yes, 8 pallets. Congratulations for the right answer. Sixth question. Again, the countdown, 30 seconds to answer. In nuclear fission, how many neutrons is or are released on the average? 2, 4 neutrons, 5 neutrons, 1 neutron, 7 neutrons. Now, very, very fast. Everyone has already voted. And yes. Congratulations all is 2, 4 neutrons. Let's see the question number 7. How an atom is made? It's made of a nucleus with protons, electrons, and an electron cloud. It is made of a nucleus with protons, neutrons, and an electron cloud. It is made of protons and neutrons, and these are double. There will be maybe some mistake, I'm sorry. And yes, it's the second one. Yeah, congratulations. I made mistake. I'm sorry, but it's the second one. I wrote the answer. But yes, the correct answer is it's made of nucleus with protons, neutrons, and electron cloud. Yes. So everything is right here. Let's move to the next question. Question number 8. Start the countdown. What are the cardinal principles of radiation protection as we saw today? Justification and dose limitation, justification and optimization, justification, optimization, and dose limitation, justification, optimization, and dose reduction. Ten seconds left. Everyone has voted, and the correct answer is justification, optimization, and dose limitation. Congratulations. And let's see, we are close to the end of the last quiz. So, how is the absorbed dose defined? So it's the energy transferred by the radiation for unit volume of tissue. the energy deposited by the radiation per unit surface of human body, the energy deposited by the radiation in the human body, or the energy deposited by radiation per unit mass of tissue? Few seconds left. Everyone is voted, and the right answer is the last one. Is the energy deposited by the radiation for unit mass of tissue. It wasn't it. Congratulations. Then the question number 10. What are the three main forms of protection from external ionizing radiation? Justification, optimization of processes and dose limitation, time protection, distance protection, and shielding materials, distance protection, protective clothes and nuclear instruments, and the fourth option, it's not there. I hope no one will click that one. Everyone has voted, and yes, the correct is the second one. Time protection, distance protection, and shielding materials. The question number 11. So the second to answer. Order the types of radiation. Start with the less dangerous, considered as external source. Alpha, beta, gamma, gamma, beta, alpha, gamma, alpha, beta, beta, alpha, gamma. As external source. Okay, everyone has voted. And yes, the correct is alpha, beta, and gamma. So let's go for the last question. It is a bit longer. So you have to order the steps to do if you discover an unconscious worker in the isotope laboratory who worked with liquid radioactive material. So you will see files are broken, radioactive materials are on the floor, the worker has a bleeding wound, as we saw in the laboratory video today. So what have to do? What do you have to do? You have to put in order these steps. You will have 40 seconds because it's a bit more complex and longer session. So it's the first step to the worker. Second step, determine and isolate the radioactive contamination on the floor. The third is to decontaminate the wound and decontaminate the floor. So you have to decide the correct order of these steps. Time's up. The correct is first to the worker, decontaminate the wound, then determine and isolate the radioactive contamination on the floor, and finally decontaminate the floor. Congratulations for the right answer, and let's see the today's results and the leaderboard. And for 2 points, today the winner are the Radiant. Congratulations. Congratulations for today's victory, and then I'll send you as soon as possible the final ranking for today. And tomorrow we will discover together the final ranking, who will win the nuclear competition for the quiz session. Thank you all for your participation. And then congratulations also. Yes, we will announce tomorrow all the awards during the final ceremony. And before saying you goodbye and see you tomorrow, I would like to share with you the link. Just 1 second. Okay, not this one. The link to another test. You got no point for your answer this time. It's just a survey, a feedback survey for the nuclear competition we held this year. So as said before, Emilia, I'm going to share with you in the chat. You can find a Google form and you can anonymously, obviously, fill it, expressing your feeling, your opinion on this year nuclear competition and suggesting improvements and so on, what you appreciated and so on. So I ask you to fill it as soon as possible. Even now, it will take no more than 3-4 minutes. I swear you. And then, so if we'll have all results by this evening, we could have also the final results for tomorrow. So I ask you again to fill this form as soon as possible by this evening. It will take very short time, no more than 3 minutes. And I think for today, that's all. We completed today's program. So I wish you a nice evening. Congratulations again. Thank you for your participation. And we'll see you tomorrow for the roundtable, as we said, for hosting our VIP host and ask her a lot of questions about nuclear profession. So I suggest you to prepare a lot of questions for her. And then for the final ceremony and all the awards. So thank you again. I send you a goodbye and see you tomorrow. Bye.
Goodbye.
Bye. Bye.
Bravo, Mattia.
Thank you, Emilia. I have to smoke a cigarette. So we have to stop the streaming. I think you can do, or we can simply leave the meeting. Let's see, because you are the